Learning Outcomes 6.1. Determine whether a system represents a low-pass filter, high-pass filter, band-pass filter, or stop-band filter. In Chapter 2, we talked about systems having an input and an output. And when the input was an impulse function, we said that the output was the impulse response. That h of t represents the impulse response, which says how our input signal is changed into an output signal. In Chapter 3, we talked about how if the input was a complex exponential, the output would also be a complex exponential scaled by h of j omega, which was a constant over time, but varied in amplitude depending on the frequency. If our input was represented as a Fourier series, a combination of complex exponentials, our output would also be a Fourier series represented by a linear combination of complex exponentials, but with a different set of coefficients. And this tied all of our different learning outcomes together. Most notably at the end, winding up that the Fourier series coefficients of our output signal would be equal to the Fourier series coefficients of the input signal, each scaled by this frequency response h. Since each of these different Fourier series coefficients is directly related to a specific frequency, every frequency is affected differently depending on our h, our frequency response. In Chapter 4, we started talking about Fourier transforms, where our input signal, x of t, could also be represented in the frequency domain by the Fourier transform of x of t, x of j omega. And our output y of t could be represented in the frequency domain by y of j omega, the Fourier transform of y of t. In the time domain, we can calculate y of t as the convolution of x of t and h of t. And in the frequency domain, the Fourier transform domain, it is the product of the Fourier transform of x and the Fourier transform of h, where h is called our frequency response. This again says that our input at a particular frequency will be scaled by a certain amount depending on the frequency to determine our output. If that scaling factor is bigger than 1, then our input x of j omega will be amplified as the output is determined. If our h of j omega is equal to 1, our output will be identical to our input. If our frequency response is less than 1, then our output will be smaller than our input. We say that our input is attenuated. And if our frequency response is 0, that means that nothing from our input is going to get to our output. Our output will be 0 regardless of our input. So our input is totally blocked or eliminated at those frequencies. This is the process of filtering, changing our input to our output depending on the frequency. It's like adjusting the bass and the treble in your car stereo. Now let's get back to these different filter types. The most common filter is a low-pass filter. For our low-pass filter, we're going to have values of magnitude 1 between negative omega c and positive omega c. Then yet at those frequencies, the values of our input signal will be transferred exactly to our output signal. We're going to pass our signal at those frequencies. We call these low frequencies because they are low in magnitude, low in absolute value, values close to 0. At high frequencies, values greater than omega c in magnitude, we totally block. High-pass filters are the opposite of a low-pass filter, where we are going to pass the high frequencies and we're going to block the low frequencies. A band-pass filter is going to have a region, a band, between some low frequency and some high frequency where we will pass our input values to our output values. And again, these filters are all symmetric around 0. Low frequencies are blocked, high frequencies are blocked. Band stop filters are the opposite of a band pass filter, where in a certain frequency band we are going to block whatever we have going on in our input to determine our output. We will pass low frequency and pass high frequencies. Notch filters are special cases of band stop filters where the pass band is extremely narrow, trying to target a single frequency as best as we can. These frequency plots I've been showing you are pictures of ideal filters where we only have values of 1 and 0. In reality, our filters do not just have values of 1 and 0. We transition between 1 and 0, or between some maximum and 0. So this is how a real low-pass filter might appear. This is how a real high-pass filter might appear. A real band-pass filter. A real band-stop filter. And, finally, a real notch filter, where a real notch filter comes down to a 0 at a point. I hope now you have a feeling for what these very special filter types look like.